join them up. This is a tiling by Pentagons. So, all of these pentagons are the same size. They're not regular pentagons, but it's because regular pentagons don't tile the plane, obviously. But these pentagons do. They tile the streets of Cairo. And then, in fact, and you can see there are two kinds of points. There's a four-valent, a tetravalent point, and a trivalent point. Let me just show you why they're the same. If you take the tiling in Johnson Park and you squeeze all of the half lines a little bit, you get the Cairo tiling. It's the same graph. It's not unique. You could squeeze it in different ways a bit, but you can't make them regular.
So it's isomorphic.
It's isomorphic graphs. Yeah. And all right. So you look at this and you say, for a point of degree 4, the coordination sequence seems to be 1, 4, 8, 12, 16, 20. How on earth could that be? This is not the square grid. How come it has the same coordination sequence? It's not the same because it has two kinds of points. Right. So we said this is a very simple fact. It ought to have a simple proof. So we came up with a simple proof. And we started out calling this a child's coloring book approach to finding coordination sequences. And we used this, by the way, to find a formula to prove the conjectured formula for the one on the postcard and for a bunch of other conjectures in the OEIS. And and it's very easy to use. It almost always, it works, and it's childishly simple. We were going to call it the child's coloring book method, but then we wanted to not run into any problems with referees, so we took out child's, and it's going to appear in Acta Crystallographica Part A very soon. So what we do is we take our graph that we start off with G, and we look for a particularly nice subgraph that we will call H. And it should have some nice properties. And you can do it with all you need is a nice big piece of paper and lots of colored pencils. And the idea is that you're going to draw this subgraph H, and it should pass through every node. So like a tree. A tree would do, but trees, there are too many trees. Trees don't really work on infinite graphs. It's very often, a particular kind of tree will do, but not always. Usually not a tree, but almost, a bit like a tree. And so one property is it connects every node to the base node. And another property is the path to the base node should be as short as you can get. So so this colored graph is our tree, is H for the square grid. And the structure of the graph is always like this. There are some specially good paths called trunks, like the trunks of a tree. And off of the trunks, there are branches, like this. And then sometimes there are twigs to make things work nicely. Sometimes there are burls, you'll see in a minute. And not only do we want these particular kind of arboreal things, we also want it to be clear that all the paths are minimal, and it should be easy to count how many paths, how many nodes there are at each distance. So this works for the square grid. You draw these 4 trunks and these green branches, and you can see that every time you move one step further, you add one more node. It's not so clear here, it's much clearer for the Cairo thing. So here's Cairo. Here's the tetravalent node of Cairo. So here's the Cairo tiling, but I've redrawn it with colored pencils. The little girl has filled it in nicely. She's colored in 4 blue trunks and then green branches like this. And you can see that we've reached every node by either a blue path or a green then blue path. It's divided up into 4 quadrants, and if we take this quadrant and stretch it out, it looks like this. And using this, you can see there are no shortcuts. This yellow dot is here. That yellow dot gets moved up there. We've straightened out the blue line. We've straightened out the green lines, the branches. They look like this. And you can see that the black lines are all the other lines that we haven't drawn. And you can see there are no shortcuts. There's no better way to get from a node to the base node other than go to the closest trunk and then go directly down the trunk. There are alternative paths, but there are no shortcuts. And the other thing is to count. Here you can see each time you move one step further away, you pick up one more node. So in this quadrant, there's 1 interior node here, 2 here, 3, and then 4 and 5. Each time you go up 1. And there are 4 quadrants, so you get 4 in. So that's the basic idea. Find a nice coloring that makes it easy to count, and there are no shortcuts. And so we've applied this to quite a lot. We've done all the uniform tilings. Oh, here's the trivalent point. This is, if you look at a point of degree 3, it has to be more complicated. It's not as symmetric. The point of degree 4 has 4-fold cyclic symmetry. The point of degree 3 has almost 3-fold rotational symmetry. Not quite, because of these twigs. You have to do this so it works. And so we only have a method, a recommended set of rules to use. We don't have an algorithm that you could program. And it would be nice if we did. This is something I'd really like someone to do. Come up with a way to formalize this so we could run this on more tilings. There are a very large number of tilings, and it would be nice to have an automatic way to use it. So our method actually gives a proof of the coordination sequence. So in this case, you do the counting, you check, first of all, there are no shortcuts by enlarging and straightening out one quadrant, and then you come up with a formula. So we actually prove the theorem that for the trivalent things, basically A of n is either 4n or 4n plus or minus 1, depending on the parity, on the value of n mod 4. That was A296368. That was a new sequence, actually. That wasn't in the OEIS. So as I said, we've done this for all the uniform tilings. There are 11 uniform, meaning transitive on points with regular. There's triangular graph paper, square graph paper, hexagonal graph paper, and then there are 8 more. And this is one of them. This is actually the dual to the Cairo tiling. This one here is the one on the postcard. And here are the remaining ones of the 11. And so there's only one coordination sequence for each one because there's only one kind of point. By definition, all points are equivalent. Now, so sometimes we have to use a burl. That's what a burl looks like. So for some of them, some of the 11, we actually had to use burls. You can see here's the 3464 uniform tiling. It has, the trunks have burls. Here are burls in the 33434 tiling trees. So Brian Gallabach has computed the number of uniform tilings. K uniform, meaning there are K, the automorphism group has K orbits on points, and all the tiles are regular polygons. And he's computed it out through 6 uniform tilings. So for these, there are 673, and there are 6 kinds of points, because it's 6 uniforms. So there are 6 times 673 coordination sequences. So altogether, there are 6536 coordination sequences for all of these. And these are all now in the OEIS, with Russ Cox's help and Brian Gallabach's computations. These are now all in the OEIS. At least the beginnings, the numerical values. So when you're processing one of these tilings, and you want to know what the coordination sequence is, the first step is to work out the initial terms. Do the counting by hand, draw some pictures, count how many points there are. Then you look it up in the OEIS, and then hopefully you're done. But if it's not there, then you try to guess a generating function using GFUN, for instance, or one of the other computer algebra systems. And then, so it gets a little harder each step. The really hard part is to prove the generating function is correct. And you can use our coloring book method. And we've done it for the 1 uniform tilings. I'm not sure if we finished doing the proofs for all the 2 uniform tilings. And there's a lot more work to be done. So here's a typical example from the RCSR database. This is the tiling that crystallographers call the KRT net. This is 2, yeah, so we haven't finished all the 2 uniform tilings. This one, it's got 2 kinds of points, a 3464 point or a 4612 point, and Joseph Myers worked out 1,000 terms of the coordination sequences, and you can run GFUND and guess a generating function. You can use the RCSR to get the first few terms. So if you ask it, it will tell you there are 2 kinds of vertices. The coordination sequence for the first type begins 467. Being chemists, they don't begin at 0, they begin at 1. So there are 4 distance, and you get this. And using the extra terms from Joseph Myers, you can guess a generating function.
Is it easy to generate many terms?
Yes and no. If you have a program that can capture the graph, then the algorithm, once you've got the graph, is easy. Let's just
So for example, this reject too many terms, this conjecture.
Yes, yes, this is correct.
But
It's just not proved.
Is proved better? This is proved or conjecture?
Conjecture, but it's surely true, because it matches 1,000 terms.
Okay.
And it doesn't have very many parameters in it. We could have guessed this, with 20 terms. But it matches to 1,000. So.
But there's no a priori reason why it should be a rational function?
Exactly, this is coming up. That's a very good question. So here, if you look on the internet, there are a lot of beautiful tilings. Look for images of tilings, tessellations, and things. And most of these we haven't studied. Yes, so your question was a very good one. The question is, the conjecture, my conjecture, and maybe many other people have conjectured it, if you have a periodic tiling of d-dimensional space, well, a nice tiling, a nice periodic graph in d-dimensional space, does the coordination sequence have a rational generating function? And it seems to be an open question, even in 2 dimensions. So that would be for a periodic tiling. You might say, what about aperiodic tilings, like the Penrose tiles, for example? And there's been some recent work by Anton Chutov and Andrei Malayev in Russia on this, and also Remy Segrist. And here's an example that Remy Segrist has worked out. He looked at the Amen-Benka tiling. This is like Penrose tiling, and there are many of them. But this particular example has a global symmetry of order 8. You know, Penrose tilings may or may not have a global rotational symmetry. But this has a unique, this particular instance of this tiling has a point, a unique point of global symmetry of order 8. And Remy worked out the 900 terms of the coordination sequence with respect to this point. But we don't have a generating function. There may not be one. I suspect there probably isn't one. But another thing is, you can look at the shape of the regions. Look at the contour lines joining points of the, so for the square tiling you get these squares that get bigger and bigger and bigger. For any of these tilings you always get increasing shells where you join points at the same distance, like in that on the postcard. And then various people have looked at the asymptotic form of these shapes, and I haven't had time to study this. I think it's a very interesting subject, and might even lead to a proof of the conjecture. So the last section, the last 5 minutes, we started I think a minute late, some recent sequences. So one thing I want to mention is that any recent submission by Eric Angelini or Remy Segrist, they're worth looking at. They have been sending in a lot of lovely sequences. And when you look at their work, you should say various things. The usual questions. Is the sequence infinite? Does every number appear? Is there a formula? How fast does it grow? And so on. And so for instance, Eric Angelini, he defined an operation. He throws out any digit that appears more than once. So if you start with 1, 2, 3, 1, 1 appears twice. So you throw out the ones, and it becomes 23. So if you start off with 1, and you keep doubling, start with 1, and keep doubling. It doubles along very nicely till you get to 16384, and then you get 6553, and then you get 32768, and then you get 65536, 65536. We've got 2 6s, 2 5s, and so we get 3. And when you're going along after 1536, you double it, you get 3072. No.
Yeah, you have that already there.
I have that. Sorry, okay. And then we get 6144, but the 4s die, and we get 61. So after 61, we get 122, and the 2s die, and we get 1. So it cycles. All right, I will. So the graph of this is what happens if you do it to the number n. And you get a very weird graph. And there are conjectures. And Georg Fischer has been looking for almost duplicates and has come up with a whole bunch of very nice problems. One of which Don Rebel and Dick Bumby solved. Another one, which I asked Matt about, was the second one here. I don't really have time to go into it. It's 2 sequences that appear to be the same. They both involve generating functions that are like partitions. And either there's a mistake or there's a theorem here of great interest. The 2 sequences, they appear to be the same, and they're both part of pairs. There's a transformation, a mapping T, which if you apply it twice, fixes 1. And a similar definition for the other one, but the conditions are different. This one has something about partitions, where the parts which are 0 of size 0 mod 5 do not appear more than once. And the other one doesn't have that condition. So I would like to know what's going on. Are these two really the same? And there's an interesting theorem. Or are they not the same? And, yeah.
So that's a partitions conjecture.
Yes.
Yeah.
This is another partition conjecture. I think this is really remarkable, if you'll allow me. You look at how many partitions of n are there into parts. They've got to be consecutive, and they're all singletons, except the biggest part, which can appear more than once. So, for instance, partitions of 9. You can have 1 to the 9th, because the biggest part is 1, and it can appear any number of times. Or you could have 1, 2, 2, 2, 2. All the parts are consecutive. So 1 and 2 and 3, and the biggest part can appear more than once, and all the other parts can only appear once. Now normally in partitions, when you look at the numbers, they're basically on a straight line. They maybe have some irregularities, but they're not scattered all over the place like this. So what on earth is going on? Well, one of the things that comes up here is, if you look at the number of partitions of n into consecutive integers, that's equal to the number of odd divisors of n, say 1, 2, 2, 7. And it's a bit of a mess. It's not anywhere near as messy as this, but it's still. I want to acknowledge the help of all the editors who keep the OEIS editing. We get so many submissions. We're swamped every day. 50 or more new sequences and many updates to existing sequences. We're swamped. So these people have helped. They're the ones who keep it running. They're the names I see every day when I look at the stack of stuff waiting to be processed. Susanna in the back row is here. Many other names, people I know very well, but I've never met. I've met several. I've met Giovanni Resta and Harvey Dale, and Bruno Berselli in Bologna, and Jörg Arndt in Nuremberg. They're spread out all over the world. Night and day, it never stops. I wake up in the middle of the night. Michel Marcuse has been editing since early in the morning in France, and so on. All my friends. And we need more editors. There's no pay, but it's lots of fun. If you're interested, stay behind and I'll give you a little demo of what needs to be done. So I'll stop.
Thank you very much.